Hi, my name is Marius, and I will today give you a brief introduction into RAWSim-O and how to use it, especially the graphical user interface. So first start it. This is what you typically will see if you start it up. And now we want to generate our first instance or layout, and this we do via the Instance tab. We press the Generate button to get a first view of the default setup and the default parameters that are loaded with just starting RAWSim-O. Now we can change basically things for our layout, which means how pods are positioned, how many there are, how many stations we have, and so on. Then settings for the scenario, so this means what kind of products and orders you're facing, so you can specify things about this, especially within this inventory configuration down here. And lastly, the controller configuration that is being applied, which means the different algorithms and strategies, policies whatsoever for the different decisions that we are facing in an RMFS system. So first I will just play around with some of these numbers to give you an idea. Hopefully most of these will have basically a small tooltip that explains a bit more about them. But for most of this, since this is still in the prototype phase, refer to the code and where it is used to get an idea of what's actually happening in the background. But for the layout, first of all, let's, for example, change the number of aisles we have. So we have the horizontal and vertical aisles, and now I want to have, instead of 8, I want to have 10 aisles. And if we quickly regenerate, then we can see that we have more aisles in this direction, basically, or just more rows, basically. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 aisles. So you get an idea of this, that these are just the aisles in between the pods. And then for the settings, for example, we want to put in 86,400, which is 86,400 seconds of simulation duration, which means that we are basically simulating for 24 hours. And we can, of course, certainly change other values in here, but again, refer to the descriptions that are in there. For example, we could change how many lines an order has, or how many number of items per line we have, and so on. And lastly, we want to change some of these algorithm settings over here, or decision rules. So, for example, for path planning, we don't want to use the far path planning algorithm, but instead, so we clear it, and instead we want to use the windowed hierarchical cooperative A* in the V version. And so we load the default setup for this one. Now we could still change parameters for this. I will quickly do it for the pod storage configuration, which is a bit more insightful, I think, or a bit more easy to understand. So pod storage means how pods, so these are stored after they are being used at a station. So there are different rules for doing this. Currently, the nearest pod storage configuration is applied, which means that wherever the pod currently is, if it needs to be brought back to the inventory, it will be brought back to a somewhat near storage location. But now we want to change it to the station-based pod storage configuration. This means that now pods are actually kept near the picking stations, or also known as the output stations, so basically the red ones over here. So we load up this rule, and we also have different settings for this rule. So for example, it's an output station mode, so that this means that pods are actually really stored near the output stations. But additionally, we also select, for example, a different rule for determining what is actually near an output station. So in here it was shortest time, so it's estimated to somewhat, it's estimated how close in time this storage location is. So this means how long does it take the robot to get there, just as an estimation. But now we want to simplify this and just stick with an Euclidean rule. So basically just they will be brought back to whatever by a Euclidean distance measure is close to the station, or to any station. Okay, so we quickly regenerate everything so that really this setup is loaded. And after we did this, we could already execute this. So this is actually currently already active. So we have the new layout, we have the new settings loaded, and this is how it's currently executing. On the right side, we can see different metrics about our simulation. So for example, we can see that the storage fill level is currently at 75%. These mean additional values like how many replenishment orders are actually inbound and so on. And then we also have some characteristics, for example, about the stations. So all of the stations are activated. We could actually deactivate some, but all are active. And below here, a lot of them are already utilized. So red means that it's currently active, and really it is either picking or replenishing in that case. And then we also see the completed orders flying through here. If we open up this, we can see all of the different orders that are currently being picked on. So we basically have, by the different colors, the different lines of an order. And in the parentheses here, we can see how many items are necessary to fulfill this line. And via the black and white color of the text, we can see whether this line is already fulfilled or not. And don't be confused, sometimes the simulation gets a bit stuck because it's actually quite fast in execution right now. And the algorithms sometimes, of course, take a bit of time for execution too, and will halt the simulation a bit. But if you want to execute algorithms that are really taking a bit more time, refer to the other tutorial maybe also, but also to the code, because there are opportunities to implement algorithms that execute in parallel to the simulation and basically feedback their results maybe after 5 simulation minutes or something like that, so that this is synchronized. Because at some point it gets unfair if an algorithm can halt the simulation time and spend 5 minutes on computing and then get back with a good answer, because that couldn't be applied in reality, of course. But there are opportunities to overcome this and basically then halt or paste the information during the algorithm execution. But this is way more advanced. Okay, for now we can see how the orders are here completed, and as soon as they're completed they are moved over here, but this list is only 40 orders long because all of the other orders are just removed because it would slow down the visualization unnecessarily. Okay, for this we also have, of course, a 3D representation. We can see this via this eye switch over here, and now we see all of the pods moving around here on the robots here. And if I go to the settings tab now, I can change especially visual options in here. So for example, for the two-dimensional details, I can go to full. We will see what that does, and then for the three-dimensional we'll go to aesthetics. We will also see what that does, and we will also see the destination of the robot where it's currently going to, and the path. And we also want to have different colors per robot. The heat mode, yeah, I can already change now. So the heat mode is actually changing the color of the pods. I will regenerate now. Because some of these things need the layout to be regenerated, and this actually, because it's not a very performant visualization, this is why I made these so that you can deactivate them, so that you don't lose as many frames as I'm currently also doing. But you can see that the racks then get basically some small lags down here. And via the color you can already see that you get an idea of what's in the pod. So a red pod is actually quite full. This is what this setting here did. So you can visualize additional information. These become more relevant depending on what you're interested in. But of course the current fill level basically of a pod is also quite easy to understand. For this, let's switch back to two-dimensional mode because it's also quite quicker. Now we can also see the graph, so we could zoom in here and even, maybe I will paste the simulation a bit. So for example, we could even click on these nodes and arcs and see basically what's the waypoint, what's it connected to, and so on. We can also click the pods and see the fill level, for example. So this one uses 492 out of the 500 capacity points. That's just one linear, one-dimensional capacity, of course. But you can see that, of course, this is a more red pod. But for example, this one is quite empty, so it only has 136 of these points that it's using. And here you can actually see the contents. So the number is just some SKU number, and in parentheses behind it, there's actually the actual quantity of the SKU that is still in the pot. And then, of course, you already noticed probably the paths the pods are planning to travel along. And depending on the path planning algorithm that is applied, you can see a full path or only a partial one. That depends. And then, of course, you also now have different colors per robot. And all right, so this should hopefully be already a bit more insightful, a bit more a quick guide to this. I will quickly regenerate the complete layout because we want to start at the beginning. You could actually, you have the option of saving the actual layout like it is. This is the first save button here. This button stores an XML representation of the complete layout like it is at this moment. So where the robots are, how this graph looks like exactly, how full the pods are, and so on. And then we can actually also store just the layout configuration. This is what I want to do right now. So I just want to store that I have a layout with 32 robots and 10 aisles and so on. I just store this in a small XML file. We will have a look at this. Then I also want to store the warehouse scenario and the order setup and so on. I do this via this yellow disk here. Also store it in the same directory. I'll put all of these configuration files in one directory. And lastly, also the controller configuration. There's always a somewhat representative name that is generated, but of course you can choose your own. Now I'm gonna go to this directory. We're gonna have a look at these individual files. So they're all XML-based files. And for example, we have this layout file. There we can see that we have 32 robots, and we also have our 10, where are they? 10 horizontal aisles that we specified. Then we also have the settings configuration with the 86,400 second simulation duration like we specified. And then we also have the controller configuration, for example, with the WHCA V-star algorithm that we've chosen. And somewhere below here, we also have the pod storage configuration that's station-based, like we specified with the Euclidean distance rule. So this is more or less everything that we use for our experiment. But in addition, and this is, pay attention to this because there are also some resource files. There's actually a file that specifies all of the SKUs that can be generated throughout simulation, and somewhat additional resource files that are sometimes necessary depending on how you configure your simulation setup. These are actually also in the repository beneath material and resources, and usually RAWSim-O tries to find these files by itself by just searching for the name. But since we're in a different directory here now for the experiment, I'm going to copy the complete resource directory also to this one. And now these should all be available. And now we're interested in going to executing the experiment, but without the visualization, which is very important if you want to do large experiments. Then you're not interested in looking at them while they're running, but only in the results in the end. And what we can do with the results, we will see later on too. So I have to move to the desktop and this folder. So we're in here, we're seeing all of these files. And now it's going to get a bit more complicated because I actually have it in a different directory here. So we're going to go over to That I could have had easier. However, okie dokie. So yeah, the CLI I want to have. The CLI is basically the command line interface of RAWSim-O, and as you can already see, it needs an instance file, which can either be an actual instance or a layout file like we've just generated over here, and then a setting and control configuration, and then also a statistics directory. So I'm going to specify these. This is our layout file that we want to simulate. Then we also have our setting and control configurations, and now we want to specify some statistics directory. Depending if you would do a very large experiment, you may want to save that to a different directory or even disk or whatever. But for now we just say it's going to be in the stats directory, so just inside this directory. And then we also want to have a seed, because you may want to do repetitions to get rid of some white noise or random noise within your experiments. And after we have specified all of these, we should be ready to go. As you can see, it's going to be generated, so the layout has just been generated, so you know about all of these nodes and all of the direction information and so on. This is just logged through the console so that you can have a look at what the resulting layout was looking like. And of course, it's in this case always a grid, and that's just the default layout. And now our simulation is actually already running, so we can see that we have a small warm-up period that we skipped for this experiment. We could specify that. However, here we can see the real time ticking. Then we have somewhat an ETA time, at what time the experiment is expected to be finished. Of course, this updates over time and depends on some steps that take a bit longer, especially during initialization. Then the simulation time, the actual simulation time. So we're already 2 hours in, and almost at least. And then the overall progress. So we specify 24 hours of simulation duration, and we have more or less an infinite set of orders and replenishment orders that are being generated. So we will cover all of the 24 hours. And here we can see the completed customer orders, the completed replenishment orders, and we also see the inventory level. And here we can all see that the robots actually and the operators at the replenishment stations filled the inventory up until 85%, where we specified that we don't want to generate additional replenishment orders because our inventory at some point gets full. This is all specified in the settings configuration. So the replenishment process actually is paused and no further replenishment orders are generated. Like I said, this is all for the warehouse scenario, and you can of course define different setups here. But in this case, replenishment stops, and now we can see that our inventory level slowly drops again, because only picking is done currently. And then we have accumulated distance of what the robots are doing or traveling. This is in meters, so the robots traveled quite far already. Then we have the number of collisions that happened so far. With the current path planning, no collisions hopefully happen anymore, because that's actually should be avoided by the reservation table overall. And then we have a small memory footprint that is kept track of, because yeah, maybe if you're applying a method that is actually quite memory intense, then you want to have insight in the end, also in the logs, of how many memory it consumed. So for now I will skip forward until the simulation is done, and then I will quickly show what one can do with the data, especially via the heat map visualization. Alright, now it's done. The experiment is finished, and now we can have a look at the results. So first of all, you can see a small outline of most relevant results, maybe. But actually we're interested in what the simulation has written out. So we specified the stats directory earlier. This is also where all of the results ended up in. Pay attention to how you name your instances and control and setting configurations. and also the seed, because this is used for the folder, the subfolder in which all of the results are written. I actually already prepared them while you weren't looking. This I did via another tool that is maybe a bit tedious to use, but use of it whatever you need, and hopefully you get a gist of what it is doing. So you can see here in the same, also in RAWSim-O, there's a data preparation tool. I will just simply execute it now. It gives you different options, but especially the first one is interesting for processing experiment results. It's not really interesting for us right now because it was only one simulation run, so we have all of the results in here, and that's kind of easy to understand. However, if you have many of these folders, then you want to maybe have a look, an overview of the results. For this, we can either choose this, or you can, however, process all of these CSV files, whatever you like. But this one makes it a bit easier. So I specify the stats directory, like you have already seen. I'm currently in it. So this is where I can just apply a dot, and I want to plot the graphs too, because I have GNU-plot installed on this machine. If not, then of course this doesn't work. But if I have, then I can start it, and this runs GNU-plot in the background with just some simple plot scripts that give you an overview for a quick insight of what's been going on during the experiment, because you haven't seen it running, of course, but now you still want to understand what happened in the scene. There's one simple graph plot out over here. That's this one. This one is maybe not so interesting. There's actually another one that gives you a lot more details. So, for example, in this one, I mean, the title now is a bit screwed up because it's kind of long. However, here you can see, for example, the number of orders that have been completed in the red graph versus the number of orders that have been placed. This is, of course, very close to each other because we specified in our experiment, I haven't told you earlier, but we specified that as soon as another order is completed, there will be a replacement order generated. So these graphs must be quite close. And for the replenishment orders, it's a bit different because we stopped replenishment operations like we've seen earlier because the inventory level got too high. That's what we actually can see in this graph. Here in blue we have the inventory level, so we see that it quite quickly got full, and then we basically stopped replenishment operations. It was full at around about 85%. Actually not completely reached, however. Then it quickly dropped again, or not quickly at all actually, but quickly refilled again. And so this is the behavior that we of course see if we have this bundle or this replenishment pause like we specified it. And also the travel distance of course changes a bit with this too, because during replenishment we have more distance that needs to be covered by the robots, because we specified that all of the pods need to be positioned near the picking stations. So this means if a robot is replenishing or is doing replenishment operation work, then it needs to bring back its pod to the picking stations that are at the east side, while the replenishment stations are at the west side. So this means during replenishment we have more travel. So this is not surprising, this is good. And we have a lot of other graphs that are generated just by default using information that we can find in the directory. And this is a bit much maybe, but gives you a first insight and helped me a lot in analyzing what's been going on in the experiment. There's actually even a real-time and memory consumed graph in here. So you can have an overview of what has been going, or what was going on. All of these statistics are within this folder or within the output results. There's one that is especially relevant if you're doing larger experiments. This is the footprint. The footprint is basically a CSV file with only one line with a lot of different information in. So about the whole simulation like it ran. For example, how many orders have been processed, how many what distance did a robot do, and so on, all the robots basically. And this is all combined throughout the 24 hours in averages or sums and so on. And these are also via this data preparation tool combined into one footprint CSV. If we would have more of these runs, then we would have additional lines in here for our experiments. But since we only had one run, we have only a header line and then an additional line for our first experiment like it ran. All right. So next we're gonna generate the heat maps of the simulation that we just ran. I just noticed that we need the actual graph or the actual instance file for this. So we go back to the instances here over here, and we still have it. I mean, we could also load it from our experiment like we defined it. So we would choose a settings file and so on, all of the other files, and just load it from the file. But since we still have it open over here, we're just saving via the blue disk the actual layout instance. Doing this now, and now we can head over to the MISC tab over here, and in this we can, in this heat maps group, first select the instance file that we just now saved, and then also heat file. This is written out in the stats and the individual results over here. We are interested in the locations polled. This is actually where the robots have been throughout the simulation. And this is typically polled at periodic intervals. I think what was the default setting is, I think, every minute or something. And this is data that we now can load back. And here we don't have much options. For the other statistics that are being tracked, you can actually choose different metrics in there. But for this one, it's just a location where the robot has been, so there's not an option here. Then we can specify additional things on how we want our heat map to be drawn and generated. I will first generate it for the first time just so that we can have a look at how it looks like. So we still see the graph because I still have it activated in the settings over here. So we see actually the waypoint layout, which is maybe not too bad for looking at where the robots have been. It's not very surprising. I will increase the opacity a bit so that it gets a bit more bold, the color. Also, I will remove these outer borders here, and now we can see basically a heat map of where the robots have been throughout simulation. Of course, at the picking stations most prominently, especially here in the queuing area. This is not very detailed, but we can of course increase this, for example, with maybe 500 tiles instead of 100 in X direction, so in width. So we update this, regenerate the heat map. Might take then a bit longer, but now we can have just a bit more granular insight or visualization of where the robots have been. This radius actually specifies how large in diameter the heat map or each pixel will be generated for the heat map. So if we increase this, then basically the heat map or the number or the locations around a pixel that are being considered belonging to this pixel is just larger. Also, we specified logarithmic scale for the value because we have a large difference in, for example, how often robots are here versus how often robots are over here. And to basically mitigate the effect, or so that we can still see where robots have been over here, we've chosen a logarithmic scale here. We want to weight by distance, so a pixel, or actually a location that we sensed within a radius of a pixel that is near the pixel is more relevant than one that is further away. And the metric, of course, is not Manhattan currently, but Euclidean. And then we could also draw the canvas in transparent so that you can render an image from this, or PNG that has see-through to or transparency on alpha channel. And then you can also specify bichromatic coloring. For example, we can choose purple and red as the two colors that will be used for rendering. And if we regenerate now, we will basically have a wider range of colors. Not for everyone, but maybe it's interesting to get a better understanding of what's going on here. For example, we can see in here that we have more, somewhat bubbles in here. This is because typically a robot in the default setting, like we've chosen, if it's dwelling, if it's not doing anything, chooses a storage, unoccupied storage locations where it idles at. And this is typically one in the middle. This rule can be modified, of course, but this is what resulted in robots hanging around here and spending a lot more time in here. And this happens if the configuration for the task allocation has a limit on how many robots it can send out to a pick station. And so you get an understanding via the heat map why the behavior, or where maybe also congestion happen, and so on. That is also what we can see over here. So these lines are actually very relevant. So we may want to choose a different setup here for the highway grid, basically, or highway part of the grid, and so on. But yeah, I hope this helps in understanding what's going on. These other icons are actually for rendering many heat maps at once, and also time windowed heat maps. So we can specify a time window, and then you would have a heat map for every 20 minutes, for example, for a simulation. This is meaningful if you switch the mechanism for maybe the pod storage rule over time. So if you start with a random rule and then go over to the nearest rule, you could do this by specifying method management configuration in here. For example, it would be a scheduled one, and then you can specify different pod storage managers. For example, here you have the nearest configuration that will be chosen after a while, and so on and so forth. You can specify all of that, and then you change the behavior of the system throughout simulation time. And this also you can then see in the graphs or in the throughput over time. This is quite interesting if you want to study these effects. I think this is most about it. Of course, maybe we also want to take a snapshot of what we just rendered. There's a snapshot button. It doesn't really work for the three-dimensional part, but for the two-dimensional it actually works quite well. It should, at least. Let's see where we have it. So in our directory where our visualization also is, we have a snapshot subdirectory, and there this new image is that I just generated. So it should be fairly high resolution, and this hopefully then is useful so that you can work with this afterwards also. Okay. I think this is most about it as a brief introduction. I hope this helps to get an idea of how to use the tool. Of course, still have to clarify it's a prototype to some extent. It came from research, so it's not perfect and not bulletproof at all. But hopefully it suits your purpose and is helpful to whatever you want to do with this. Thank you very much for your attention, and have a great day.